On my Maker channel, I have started a series called Tools from the Maker's Tool Belt. The idea is to provide techniques or tools that you can use in your projects to give them a new feature or a wow factor. The first video covers how to add voice control to your project by emulating a Philips Hue bridge. Below, I provide the link to the video where I walk through exactly how it works. Like Alexa, set nuclear reactor to red, or set nuclear reactor to turquoise. This video is a companion to that video where I'm going to walk through the Arduino C++ source code that runs on ESP32 to make all this magic happen. Welcome to MakerAtPlay Coding, where I share my adventures in programming. If you're new here, I'm Michael, and in addition to being a coder, I'm also a maker and share my projects on this channel and my other two channels dedicated to electronics and woodworking. You can find links to those channels below. If you're a fellow coder or maker, I would love to have you as part of the MakerAtPlay community and hear about the projects that you're working on. Arduino has made it very easy for people to code without having to know too much about C++ by having the INO file handle some of the complexity for you. And therefore, most of the examples you see online put all of the source code in the INO file. But this really isn't the best practice when programming. Therefore, in my projects, you will see me organize my code across many source files. In my videos, I want to help people improve their programming skills beyond the beginner level and grow beyond the practice of just using the INO file for your whole program. Also keep in mind that I'm writing my code to prioritize readability first and performance a close second. I don't want to make the code too hard to understand just to save a little memory or a few CPU cycles. Now let's walk through the code that makes an Amazon Echo believe that our device is a Philips Hue bridge. There is a link below to the GitHub repo for all the source code that I'm about to walk through. I have broken this project into two main objects, the HueBridge class, which handles all of the API calls we need to support, and the UPNP class, which handles all of the UDP messages to support the discovery of our device. I wrote a simple JSON parser as a helper class to simplify some of the API functions. There are two header files that define some string constants to make the code cleaner, and finally there is the INO file that acts as an example program to see how all this works. Again, I suggest you watch the companion video as it walks through the flow of network messages, which will make it easier to understand this code. We start with the UPNP class. This class is going to listen for incoming UDP packets and process them. In the init function, we begin listening for multicast traffic on port number. This port number is defined by the Simple Service Discovery Protocol. The handle UDP function gets called from the main Arduino loop so that we are constantly looking for UDP traffic. If we receive a packet, then we are testing to see if it is a msearch message. If it is, then we will call the send UDP response function that will send the necessary message back. I use the printf function to format the response message, which needs to be customized with our IP address and a unique ID, which we use the MAC address for. Once the message is built, we send it to the remote client's IP address and port number, and that's all there is to the UPNP logic. Now let's look at the HueBridge class. The HueBridge class is what implements the necessary APIs that an Amazon Echo will call when it thinks it is talking to a real Philips Hue bridge to control and extend the color lights. The HueBridge class provides 5 public methods, 3 of which are required to be called from the main program in order to make this work. The use of the remaining 2 methods depends exactly on what you do in your project. First, we call the addDevice method to tell HueBridge class exactly how many lights we want to expose to the Amazon Echo and what their names will be. In this example, I just call it once and create a single light called nuclear reactor. You can choose to call this method more than once to add multiple lights with different names. As we can see here, this method is going to create an object to hold the details of the light and its current state and keep them in a vector. Now that we added a light, next I call the onSetState method to provide the HueBridge class a callback function that a class will call anytime that the state of a light changes. This most commonly happens when we give Alexa a command to change our light. This callback function is where you would put your code to implement the logic for your device. For example, this is where the code goes to turn on or off an LED. In this example, I'm just writing the data to the serial monitor. Next, I call the start method on the HueBridge class. In this method, we can see that we start a web server and tell it what API endpoints we want to handle. I also have some logic in here to enable cores so that I can access this APIs from other web pages not served from this ESP32. And I also initialize the UPNP class so that it will start listening for discovery messages. The final thing I need to do in the INO file is to have the loop method called the HueBridge handle method, which allows web traffic and UPNP traffic to be processed. Now let's talk about the private methods of the HueBridge class. As we see in the start method, most of the remaining methods in this class are callback functions that handle when one of the APIs are called. The first one we see handles the get call to the description XML file. In this method, we load the description XML string that is defined in the template header file and replace necessary values in the XML using the printf function. And we return the string as a response to the API call. I have added comments at the top of each of these API handler methods to provide sample input and output for reference. The next handler method handles the API endpoint to create an authorized user, which is part of the security model for the real Philips Hue bridge. Here you can see that I'm responding with a static username of user ID, which works. If you want to make your device more secure, you can change this code to have more logic. For example, the real Philips Hue bridge returns a dynamic username, but only if the physical button has been pressed on the device. The next two API endpoints share the same callback function, as they do almost the exact same thing. First, we check for the presence of an integer in the URL after lights. If there is no number, then we will return a JSON string with all the lights in our vector. Otherwise, we return the JSON for just one light whose index in the vector matches the number provided in the URL. We use the device JSON helper method to build the JSON string that is defined in the template header file. Notice that this API handler doesn't have any logic to validate the user ID. So if you plan to add more security, you would need to add that logic to each of the API handler methods. The next API handles a put that sets the state of the light, like turning it on or off, or setting the brightness or the color. We start with some basic error checking to make sure we have a body and a valid light ID. Then we use the simple JSON parser I wrote to look for different properties that the Amazon Echo could send us. The on property is a boolean that is present in every call from the Amazon Echo. Bree is the brightness value that is sent when we tell Alexa to change the brightness of the light. CT is the color temperature value that is sent when we tell Alexa to make the light warm white or cool white. And hue and sat are the color values sent when we tell Alexa to set the color of the light, like setting it to red. I have put logic in here to check if the property is present, otherwise set it to 0, as the 0 has special meaning in my setState method to not overwrite the current value. I need this logic because values like CT are not sent with every message from the Amazon Echo. And if we return a value of 0 in CT in the getLights API, the Amazon Echo will take that as an error and tell you there is something wrong with your light. In fact, I learned through a lot of trial and error that the CT property needs to always be returned with a value from 153 to 500, and the mode property must reflect the correct value given the command Amazon Echo just sent to set the state. If the Echo changed the color temperature, mode should be sent back as CT. Else, if it set the color, then the mode should be set to HS. Otherwise, the Echo will report an error to you. And then we build a response JSON that shows what properties we set. For my testing, it doesn't seem that the Amazon Echo cares about this response, but I still code it to match what the real Philips Hue bridge returns. And here we have a handler for the root path that will serve up a web page that allows the lights to be controlled in a browser. This method returns a static string that is defined in the template header file. The string is rendered as an HTML page in the browser. And I also added a handler for the debug clip HTML file that is just like the same page on the real Philips Hue bridge that allows you to test the API calls. And these are the APIs that make it all work. To see this used in a real project, check out my on-air sign. I will provide a link to that project video below. Hope you find this code useful. Now go build something awesome and let me know about it with a comment below or tag me on social media.